Suppose we're given some matrix A. To see what this matrix does, we can visualize how it transforms different vectors. Now suppose we're asked to find an orthogonal set of vectors that when transformed by A will remain orthogonal. One way to do this in 2 dimensions would be to start with an orthogonal set of vectors and then keep rotating them till we notice that their corresponding transformations are also orthogonal. At this point, it might seem like such a set of vectors doesn't exist for this matrix. But we weren't really able to see all of the transformed vectors because some of them were too small. So let's try this again, but this time we'll normalize the transformed vectors before we plot them. And there it is, an orthogonal set of vectors that does indeed remain orthogonal when transformed by A. This set of vectors is what defines the singular value decomposition of A, and I'll restate that more clearly in just a moment. Now, if we wanted to do this in higher dimensions, this search method would become very computationally intensive. So let's see if we can find a simpler solution to this problem that doesn't involve searching. First, let's restate our problem. We want to find an orthogonal set of vectors that when transformed by our matrix will remain orthogonal. In 2 dimensions, this means we want to find a v1 and a v2 and a y1 and a y2. Let's also split up the y's into a direction and magnitude so that u1 and u2 are unit vectors. To make this analysis more general, we can rewrite our problem in matrix form. Now the goal becomes to solve for a v and a u that are orthogonal matrices. If we find these matrices, then we say we found the singular value decomposition of our original matrix A. And the reason it's called a decomposition is because we can write A in terms of u, sigma, and v. Okay, now let's see if we can solve for u and v. First, we'll multiply both sides by A transpose and expand out the terms. Because the u we're looking for is an orthogonal matrix, we can cancel out u transpose u. And since sigma is a diagonal matrix, we can just square all of the terms in the diagonal. Now we start to notice something interesting. It looks like V is given by the eigendecomposition of A transpose A. And our condition that V be orthogonal is satisfied because A transpose A is symmetric. And the eigenvectors of a symmetric matrix are orthogonal. Similarly, we can find U by right multiplying our expression by A transpose. Let's summarize what we have so far. We wanted to find a u and a v that satisfy this expression but are also orthogonal. We found that the eigendecomposition of A transpose A would give us an orthogonal matrix V. And similarly, we found that the eigendecomposition of AA transpose will give us an orthogonal matrix U. One last thing to note is that we've also essentially proved that the eigenvalues of the matrix A transpose A are going to be the same as the eigenvalues of the matrix AA transpose, because in both cases, we started with our original equality, then made the right-hand side look like an eigendecomposition, with the eigenvalues being sigma squared. As it turns out, one of the interesting properties of SVD is that it answers the following question. In what direction does our matrix stretch a unit vector the most? In mathematical terms, SVD solves this optimization problem. To see why, let's first change this problem to this one. The two are equivalent, because finding an x whose transformation has the greatest length is the same as finding an x whose transformation has the greatest length squared. Now let's write out the eigenvalue equation of matrix A transpose A. Since x is a unit vector, we can cancel out x transpose x. So maximizing x transpose AX is equivalent to maximizing lambda. And to maximize lambda, we can simply choose x to be the eigenvector with the largest corresponding eigenvalue. And if you recall, the columns of the matrix U are the eigenvectors of the matrix A transpose A. So the eigenvector of A transpose A with the largest corresponding eigenvalue is going to be the first column of U. So once again, we are able to use the singular value decomposition to solve a problem without having to do a search. This is why SVD is a very useful decomposition to compute for a matrix. In the next video, I'll go through yet another problem that can be solved using SVD, which involves finding the directions along which a dataset is mainly distributed. Solving this problem is known as principal component analysis.